prove the Lagrange remainder theorem, we first need to derive Cauchy's mean value theorem, which states that if f and g are two functions which are continuous on a given interval, and differentiable, except possibly at the endpoints, such that the derivative of g is non-zero for all x in the interval, in that case there exists a value in the interval which satisfies the result here. We won't prove this theorem, but we'll look at a geometric interpretation. What we'll do is plot f of x on the vertical axis and g of x on the horizontal axis. Then, as x changes, both f and g change, and the coordinates of f against g follow a meandering path through the plane. Now let's pick some value of x, which we'll call a, and some value of x which we'll call b, the shaded part of this contour represents the range AB. If we join up these 2 points with a straight line, then the slope of the line is given by f of b minus f of a over g of b minus g of a, which is this quantity that we've got here. By considering lines parallel to this one, we can see that there exists some point xi, which is in the interval from a to b, where the tangent to this contour has the same gradient. And by the chain rule, this gradient is equal to f dash of xi over g dash of xi, which motivates the result. Now, to prove the Lagrange remainder theorem, we'll start with an expansion of a function f of x about the point x equals alpha. And we'll truncate the expansion at degree k. Instead of taking a fixed alpha and varying x, I'm going to look at what happens to this expansion as we change alpha for a fixed x. So I'll call the expansion big F of alpha. Notice that we have f of x equal to the exact function value, since all of these terms go away, and that f of a is the truncated Taylor polynomial about x equals a. We want to find f of x minus pk of x, the remainder in the truncated expansion. And this is the same as f of x minus f of a. We now invoke Cauchy's mean value theorem here to rewrite this as f dash of xi over g dash of xi multiplied by g of x minus g of a, where xi is in the range from a to x and g is some function which satisfies the restrictions of Cauchy's mean value theorem. The reason that this all works out so nicely is that if we do differentiate the function, we calculate f dash of xi, it turns out that most of the terms cross-cancel, and so we're left only with the k plus 1's derivative of xi multiplied by x minus xi to the k over k factorial. You can verify this result as an exercise. It's then convenient to put g of alpha equal to x minus alpha to the k plus 1, and substituting into here gives the result.